Today we're happy to have Daniel Harlow, all the way from MIT, tell us about symmetries in quantum field theory of gravity.
Yeah, so thanks for the invitation, and welcome everyone to this, at least, corner of this country, which is still hopefully not totally insane. I was asked to do a review of some older stuff, so I dutifully will do so. But I try to spice it up a bit here and there with some newer things, just because I know many of you have heard me talk about this before, probably multiple times. Symmetries in quantum field theory and gravity. So I'm going to try to give an overview of an approach to the idea of what is symmetry in field theory and gravity. How do you define it? Which I and others have been developing over the last decade or so. And so the idea is to use algebraic methods to say what you really mean by a global engaged symmetry. After which, once you have all the definitions set up, then you can use holography to think about the sort of classic conjectures about symmetry in quantum gravity, namely that there should be no global symmetries, that you should have completeness of gauge representations, and that the gauge group should be compact. And okay, so since I have the fortune of going after Leonardo, I'll mention that the word gauge appears in two of the conjectures. And so apparently the word has to mean something, because if it wasn't there, they wouldn't be correct. And so this is based on a bunch of things, kind of various papers by me and also Hiroshi, Edgar, who's here. I didn't know that. Somewhere there is Edgar. And also Tokiro, earlier work by Tom and Seiberg on this. And then there was a bunch of papers trying to put bounds in the first case on how much the symmetry needs to be violated in order to avoid a contradiction. So here's a plan for today. So I feel that the honor of the algebraic approach was a bit maligned yesterday, so I'll start by saying a little bit about it, since certainly it's central to everything that I'll say here. And then we'll talk about, well, what is a global symmetry? What is gauge symmetry? We'll talk about no global symmetries in ADS. Talk about no global symmetry coming from the unitarity of evaporating black holes, which is good because, we don't live in ADS, but we do have black holes, and we hope they evaporate unitarily. Actually, I'm not going to talk about completeness. I should have removed that. And then I'll say a bit about this issue of gauging space-time inversions. So for example, symmetries like time reversal or CRT symmetry in gravity have to be gauged, and that leads to some strange things that I'll say a little bit about at the end. Now, I'm actually not, I don't feel the need to actually get through all of this, so maybe I'll have this sort of anti-Tom philosophy, so, whatever, interrupt me whenever you want. I don't care. I'm here to entertain you guys. This is not about entertaining me, so whatever. Yeah, anything you don't like, just let me know, and we can work it out together. Okay, so first, why algebras? Okay. So, here in the U.S., right, well, of course, the most traditional axiomatic approach is to just not think about the axiomatic approach at all and compute Feynman diagrams. Okay, but that's not us in this room. We like to actually understand what we're doing. And the traditional approach was the sort of Streeter and Whiteman approach, where you look at the analytic properties of correlation functions of local operators, which are really operator-valued distributions. And in conformal theories, this approach was extended to the bootstrap, where you look at correlation functions of local operators, you talk about analyticity and crossing and what have you. Now, unfortunately, I would say this approach, certainly as originally formulated, has very severe deficiencies. it allows things which obviously are not field theories. So one that Tom mentioned yesterday was you take a field theory and you restrict all the correlators to a hyperplane. Okay, and that obeys the Whiteman axioms. But I mean, come on, right? Another example is you take a theory with a global symmetry and then you just restrict to the singlet sector under the global symmetry, and that gives you a set of neutral operators which obey the Whiteman axioms. You also can't access global information about the theory, such as the topology of the gauge group. What's the difference between SU2 and SO3? What's the difference between U1 and R? And there's also no way to talk about information theoretic notions such as relative entropy and mutual information, which I would say have become clear are useful things to talk about in field theory. And then certainly once you couple to gravity, entropy is what you talk about all the time. Now, in 1+1 CFT, these problems aren't so bad. There's a fix, which is that you say that the theory should make sense on the torus. Okay? And that somehow accesses more of the local structure of the theory than you get just from the correlation functions. But if you try to extend this to higher dimensions, it just becomes kind of, I said clunky and incomplete, I guess, are the words I used here. You want some kind of gluing rules to apply, but what exactly they should be, I'm not sure. And also, if you want to actually, in a particular theory, do calculations, this is a pretty inefficient way to think about doing it.
Can I make a comment?
Yeah.
Of your three criticism, I think the only one that I would accept is the third. Because the first one, well, the stress tensor is not there. So that's something. That
helps with the first counterexample, but it doesn't help with the second.
Well, but again, as you say, you're sort of criticizing a straw man. Nobody says that we should always just do RD. We can consider other topologies. And the way
I mentioned that here, right?
And the way you'd address point 2 would be to consider difference. We can consider conformal difference. There's a perfectly good way to extend the axioms in the presence of defects, boundaries, interfaces.
Well, I would say that's still in the end going to other topologies, right?
Yes, absolutely.
Yeah, so I agree that there's a way to try to get at this by going to other topologies, but I don't think there's a complete set of rules. And yeah, I don't know. I mean, it just.
I completely agree that this is not the whole story, but it's.
I mean, in 2D we kind of think that the torus is enough, but in higher dimensions, no.
Well, there are theorems.
Yeah, that's right. Yeah. So sorry, I'm not putting all the references. Greg.
No. References. Saying that theorems.
Yeah, that's right.
Not kind of think.
Okay, all right. So I apologize for not having insufficient conviction. There's too much conviction these days. I'm trying to.
So we don't disagree, actually.
Yeah. I mean, okay. So I don't. I'm not saying we should take this and throw it in the dustbin, right?
But also because we can compute things in this approach, whereas in the other approach,
no, you can. No. So to me, okay. I haven't yet said. So see what I say about the other approach. Okay. So now what about the algebraic approach, right? So this one is more from Europe, is my understanding of the history, and I think it gives a much more elegant way to impose. These more subtle consequences of locality, which are not captured by the Whiteman approach, and in a way where you never need to think about other topologies. It's enough to just study everything in the plane. So here's how I think about it. So just as we can turn a set into a topological space by giving it some additional structure, the structure of saying which are the open sets, we can take a quantum mechanics theory. So a quantum mechanics theory, right, it comes with a Hilbert space and a Hamiltonian, and that's it, okay? But we can give it some additional structure, which a general quantum mechanics system wouldn't have, which is the net of operator algebras. just as, in a topological space, there's a set of, you have to say what the open sets are, and then there are rules that the sets of open sets has to obey. Similarly, in algebraic field theory, there are rules that the net of operator algebras has to obey in order to make a valid quantum field theory. And so the basic idea is that for each, and here I'm not trying to be rigorous here, and by the way, I should say that, I think one of the issues with this approach sociologically is that people got the idea that the point of it was to try to be rigorous about quantum field theory. Okay, that's not the point. The point is to understand quantum field theory. Okay, and great if you can be rigorous about it, but that's not the point. The point is to understand. Okay? Right, so what is the structure of the net of operator algebras? So the idea is for each space-like region R, you associate an algebra A of R, which is a subset of the bounded operators acting on the Hilbert space of the theory quantized in Minkowski space. And here, when I say RD, I mean Lorentzian. Okay, yeah.
Just a quick question. So when you say there's no need to consider other topologies, the entire space-time is assumed to have trivial topology.
Yeah.
But the R, the regional R you choose, can still be topological.
That is correct. Yes, that is correct.
So that's effectively introduced non-trivial topology to the.
No, but I never need to go to the Hilbert space of the theory on other topologies. Everything is in the Hilbert space that Whiteman talked about. But I can see all that stuff in Whiteman's Hilbert space.
But
That's the
there's
point.
still non-trivial topology on the table.
Well, in some sense, yes, but that's the strength of it, right? Is that it's all living in Hilbert space. You never need to change the theory from a quantum mechanics point of view.
Pretty limited in what topologies you can have, right?
Of the regions
The region
R.
R must be an embedded region of RD.
Yeah, that's correct.
So
That's correct.
you'll miss things. For example, you can never make a topological space with torsion in its cohomology.
Yeah, probably not. Yeah. Okay, and so like I said, just as with open sets, right? These algebras.
Three dimensions.
Well, and high
I knew that you were going to start.
I know better than to get into an argument with you guys about
But it's
discrete torsions.
3 dimensions. That's true. It's true.
So just as with open sets, right, there's a list of natural properties that the algebras are supposed to obey. And this is not an exhaustive list. It's just 3 that I'll mention. So they have names. Sorry, I didn't write the names because I was running out of space on the slide. So if R is contained in R prime, this should be A of R here, sorry. A of R is contained in A of R prime, so that's called nesting or isotony. So here prime of a region indicates its complement. So then the algebra of the complement of R is equal to the commutant of the algebra of R. That's called duality or Hogg duality.
What's the causal complement?
Well, yeah, okay, we can discuss whether, I said R was a space-like region. If we want to take its domain of dependence, then it's what you said. Yeah, but I'm just thinking, put them both in a Cauchy slice.
R is an open subset of
A Cauchy slice.
Cauchy slice.
Yes.
It's not an open subset of Minkowski space.
Yeah, but if you want to be more covariant, you take the domain of dependence of that. Yeah. Okay, and then finally, this one I'll call disjoint additivity. It says that if R1 and R2 are disjoint spatial regions, mutually spatial, then the algebra of the union is the union of the algebra. And so now sometimes people demand that for all regions R1 and R2 without necessarily being disjoint, but that's too strong. For example, that rules out Maxwell theory. But for disjoint regions, this had better be true. It's basically saying if I have a region here and a region there, then the algebra in the union is just built out of the stuff living here. So that's a manifestation of locality. Yes?
Yeah, I know you're not being rigorous, but do you really want to talk about an infinitely thin time slice in quantum field theory?
Yeah. So in this approach, yes. I mean, but the operators don't live just in the region R. I didn't tell you how A of R is defined. The rule is you take its domain of dependence and then you smear the operator value distributions in the domain of dependence of the region.
Oh, okay.
Yeah.
Algebra, does algebra mean von Neumann algebra?
Yes. Yeah. So I mean, I could say a lot more about other rules that it should obey and exactly how these algebras are defined, but that's not the point. The point is that this is helpful for thinking. Okay. And so let me just do a few examples so you can see the power of this. So
Sorry, is this, for example, are you, in 1 plus 1 dimensions, will you recover modularity just by thinking about
yes.
the spatial slice?
Yeah, I think so. Yeah. Yeah, and I think I'm going to give an example of that here. Okay. So, so here are a few examples where you can see the power of this. So one thing that you rule out with modularity, but not with just looking at correlation functions of local operators, is this idea of the singlet sector theory. Okay. So consider the singlet sector of some theory with a Z2 global symmetry. It doesn't have to be Z2. I just do Z2 to be easy. Okay. And let's say that there's some operator O in the theory that's charged under the symmetry. So of course O is removed by the singlet constraint, but I start with a theory that has a O that's charged. Okay. So then I take two disjoint spatial regions R1 and R2, and I can make a neutral operator O of x1 times O of x2, where x1 is in R1 and x2 is in R2. And this is a neutral operator, because it's a product of two O's and that were charged under Z2. Okay? So this is an element of the neutral algebra in R1 union R2, but you can't build it out of the neutral algebras in R1 and R2 separately, because then you would have had to use the charges, so that violates disjoint additivity. So that's an example where you see you get something that you might have thought you needed the torus to get.
Sorry, maybe this is different, but people propose that the singlet sector of the critical O model corresponds to higher spin gravity.
Yeah, I don't believe it, because that's not a local theory. Yeah. It's true people said that, but that doesn't make it true.
Well, but you can count the Chensanos, blah, blah. I mean,
But then then it's not Vasiliev, right? Then there's extra degrees of freedom and you get in trouble on the torus. Yeah. Yeah. Yeah, so this is an example where disjoint additivity is capturing more locality than you would get just by looking at the Whiteman axioms. Another example I like is thinking about Dirac quantization in Maxwell theory. So say you're given some spatial disk. It's a two-dimensional disk in Minkowski space. So for any real number q and real number q tilde, I can define a Wilson disk and an 't Hooft disk like this. I integrate over the disk of f or star f. Okay, and since, you know, to see that it's the Wilson line, right, f equals dA, so you use Stokes' theorem, and it's the integral of a around the boundary of the disk. But I can also just put f there. And so look, these are gauge invariant, clearly, because I just made them out of f and star f. And they're gauge invariant for any q and q tilde. Okay, so what do we mean when we say that q should be an integer or q tilde should be an integer or something? These disks are totally fine in Maxwell theory. But the issue is that you can consider an annular region which contains the boundary of the disk but not the disk. And then you can ask, is there a sense in which I can assign some of these operators to just live in that annular region containing the boundary of the disk and not containing the whole disk? Okay? And if you want to do that, then your assignment of operators needs to be consistent with the axioms that we discussed of the operator algebras, right? And so what, in particular, if I have an annulus like this and an annulus like that, and they're linking with each other in space, okay, those are space-like separated regions, and so by Hogg duality, the operators in them have to commute. And so imposing that says that you can only make this assignment if q times q tilde is 2 pi over e squared times an integer for some fixed constant e, okay, which is Dirac quantization, and this constant e sets the radius of the gauge group. So by specifying the algebra in this annular region, you have identified the global structure of the gauge group and also derived Dirac quantization, which I think, again, would be very challenging to just try to get from local operators in the plane. Okay, so maybe I'll stop there.
True, but of course, the moment you include line operators, then you can have a discussion.
No, that's exactly the question. So when you say include line operators, you need to give me a rule for what's the difference between a line operator and a disk operator. I can do that. I'm not sure if you can do that. Yeah. I can do it even just on the plane. I can actually tell you. And it's not, you know, so for example, people like Seiberg or whatever, sometimes they say that the ones with the wrong q and q tilde don't exist. Okay? Look, they exist. Here they are. You can't fight with them. You know, as operators on the Hilbert space, they exist. If you want to criticize them, you have to say in what sense.
Well, that's a symmetry operator ending on an operator quantized model.
No, but it's a fine operator, right?
Yeah, it is. It's just
when you say it's a line operator, what you mean is that it's an element of the algebra in the annulus, okay? And then we have to make sure we can consistently assign that preserving Hogg duality. Okay, that's how it should have been said all along, and there's been a lot of confusion in the literature because people didn't say it that way. Yes.
I think that the distinction between genuine and non-genuine line operators in this Seiberg story can be understood if you think about twisted sectors.
Yes.
So
Yes.
the
I mean-
line operators that are non-genuine are really endpoints of a symmetry defect, so they live in a twisted sector of the theory, not in the.
No, but these are so these as disk operators. These are perfectly genuine. Okay, and it doesn't matter what the radius of the gauge group is.
They're
they always
genuine
exist.
disk operators.
Yeah, they're
They're not
disk
genuine
operators.
line operators.
No, but I don't understand. An operator is a map from a Hilbert space to a Hilbert space. It's what is this genuine or not genuine? The only question.
Attached to a topological surface, right?
No, but
There's a perfectly good way to rephrase your criticism in the other approach. You're criticizing a straw man. I mean, you may prefer this language, but the other language is equally rigorous for this purpose.
I'm not saying that people don't understand this.
Yeah.
Okay. I'm just saying that I think this is a much more elegant way to state what's going on.
That
Okay.
could be, but-
Because you only need one set of axioms and everything is correct. You know, you don't have to case by case kind of go through and use the word operator in this sloppy way where sometimes it's a map on the Hilbert space and sometimes it isn't. Okay. Anyway, I don't want to give the whole talk about this. Sorry, one more.
I have a question about the first one. So
Yeah.
in the case we restrict to a single sector, is there some ambiguity in what we mean by A of R?
No, there's never an ambiguity. It's part of the definition of the theory. Just like with the topological space, you haven't defined the theory until you say what the operator algebras are.
So like let's say we think about Ising symmetry in the first case and
Yeah.
restrict to the Z2 sector. So I can have a
No, but
pair
you
of-
can-
In how many dimensions?
in 1 plus 1.
Sorry, but you can gauge. Of course, you can gauge the symmetry.
Yeah,
right?
but let
But
me
if you
not-
gauge the symmetry, that changes the theory.
I know, but let me not gauge it. Let me just restrict to the Z2 even sector. as
So
an
you,
example.
you don't here with Z2 you don't mean fermion parity. You mean the global.
That's right. The
Good,
Z2
okay.
of the Ising boson.
Yeah, you can do that. Yeah,
So I can have a pair of twist fields, right, connected by some Z2 line.
yeah.
But since we restrict to the Z2 even sector, I might as well connect them through the other direction, right? Because the entire
No, that's just like this example, right? The line is really there, okay, in that theory, and so that thing is not an element of the algebra of the union of the two disks because there's a line that doesn't go in the two
Right, but-
disks, and you can detect it.
So let's say our space is a circle. Does it matter if the line goes this way
Yes,
or
it
that way?
matters.
I see.
It matters.
So we treat them as two different
They're
objects.
two different operators. Yes.
A related question is that does the first example also violate Hogg duality or not?
I think it doesn't.
You think it
Yeah,
does?
I think it doesn't. Yeah.
Okay, I have a related question. So, the Ising model with just the one in psi. Okay,
Yeah.
One in the one. So, leave out the spin field. Okay, and so, but you're working on the plane.
So you mean the Majorana, just the,
Yeah,
the
just the
ungaged
Majorana,
Majorana?
yeah.
Okay.
So,
Fine.
are you going to tell us does that satisfy these Hogg axioms?
Yeah, although you have to be a little careful about when you talk about the commutant. You have, because when fermions commute, really they anti-commute, so you have to grade the
that's
definitions.
not a
But
problem.
if you grant me that, then yes.
Yeah, of
It
course.
obeys.
Right,
Yeah.
but that theory is not modular invariant if you don't include the spin field.
Sorry,
That theory is not modular invariant if you don't include the spin field.
no, I think you have to discuss what you mean, right?
Well, I mean,
So
if you make a modular transformation of the conformal blocks of the identity and the Majorana fermion, it's not a representation of the module.
sorry, you mean because of the rotation, because of T?
It mixes into the spin.
Yeah, no, but
You're not going to get a modular invariant
No, but you just
partition
have
function.
sorry. When you
Torus.
do it, when you have genuine fermions,
Yeah.
it's a rotation by 4 pi that should be 1, right? So of course, the rules should acknowledge that.
Yeah, that's fine.
But
I don't think
this
that's
is
that solves the point.
A Majorana fermion is a fine quantum field theory. We just have to define things to respect the fact that they're fermions.
Ah,
Yeah. I mean, that has to be baked into the axioms that fermions can be there, right? As I said with the anti-commutativity.
so you're going
and
to
so
say that it's a spin theory.
Yep.
Yeah.
And if I
Yep.
look at the representation, you're saying it's a representation of gamma of 2 that
That's
preserves the spin.
on. That's
spin.
correct, yes.
Okay.
So
Yeah.
just one quick question.
But-
So in the first example, what would we say about the Z2 operators that wraps the entire line?
Sorry, which example? Now we're back
First-
to doing
the
the
first
gauged
one.
Ising, the Ising where fermion parity is gauged.
No, just Ising restricted to the Z2 even sector.
No, I
not
think
gauged.
that has this problem, right? So then there you use the spin operators, right? So I would say in the true Ising, the spin operator at point x1 is in the algebra A of R1.
Yeah, but no, I mean the Z2 even sector of Ising.
That doesn't obey.
Yeah, that exactly is an example of this, right? Because
so
I take the product.
I
of two
understand
of
it
them.
violates the disjoint additivity, but
Yeah.
I want to ask, what would we say about the Z2 line operator that wraps the entire space? Is that because that commutes with everything in the algebra, right? Because by definition you restrict to the Z2
Yeah, so I
even
think you
sector.
say it's a C number.
Oh.
Yeah, it's proportional to the identity in this theory, I guess, is what you have to say.
But if you say that, then the pair of twist operator wrapped around this way is the same as that because they differ by a C
I'm
number.
not sure if you say that. Yeah, I'm not sure. I'm not. Oh, sorry. You mean in the singlet theory? Do I say that? I certainly wouldn't say that in the truth theory.
No, in the singlet theory.
I just draw out the singlet theory. It violates one of the axioms, right? That's like having a topological space where the union of two open sets is not open. We just don't talk about it, right?
Okay, yeah,
Just
I
don't
agree
talk
it
about
violates this axiom. I just want to see if it's even worse that violates other axioms, such as...
Okay, probably, but it
Okay.
violates this one, so it's not a quantum field
Okay,
theory.
sorry.
Yeah.
Okay, fine.
All right. I should talk about the organizers told me to talk about at least a little bit. So, okay. Well, okay. Actually, okay. But we can continue. Okay. So now okay. So what do we mean by global symmetry in quantum field theory? Why did I talk about this stuff? It's because the definition uses the algebra. So I don't know how to give the definition without using algebras. So here's my definition, and following Leonardo, I'm going to talk about internal zero-form global symmetries. Okay, so I said it once, I won't say it again. You can generalize everything I say, but it's just, let's keep it simple. Okay, so I say it has a global symmetry group G if the following four things are true. So when you quantize in Minkowski space, so the spatial manifold is RD minus 1, there's a unitary representation of G on the Hilbert space. Hopefully we're all okay with this one. You never know, but yeah, go ahead.
Sorry, in your previous slide, you had a single Hilbert space. You were thinking of the axiom system where you're on a fixed Minkowski spacetime.
Yeah, I'm still in that here. That's why I said
So
I'm
the
in.
words quantizing on a spatial manifold, you just mean the Hilbert space we're talking about.
Yeah, I mean the Hilbert space that we're talking about. Yeah. I'm going to need to go to the sphere in a minute. Because to do ADS-CFT, but yeah. I mean, to be clear, I have nothing against other topologies, right? I believe in gravity, and so it better make sense to couple to other topologies. It's just I postpone it as long as I can. Okay, we better have a unitary representation of the symmetry group. Okay. Okay, now here's where the algebra shows up. So just as in a topological space, when you have a function and you want to say it's compatible with the topological structure, it needs to be a continuous function, one that respects the set of open sets. So similarly, in quantum field theory, a symmetry is only interesting if it respects the algebraic structure of the theory. And so in particular, it means that the algebra in any spatial region R is closed under the symmetry. Okay, so maybe I should use a word like outer automorphism here or something, but anyway, you conjugate by U.
Inner.
No, because this U on the whole space is not a member of the algebra for. Okay, so I think I said it right. I don't know. Yeah, so the algebra should be preserved by the symmetry. Again, I think that's non-controversial. Some people like to write about things where it's not true, but okay, I don't think it should be controversial.
This could be inner, right? If the symmetry operator is random.
Yes, or if I just take R to be all of space. Yeah, so it can be, but it doesn't have to be. Okay, then I want to make sure I identify the symmetry group correctly. So I demand that for any G which is not the identity, there's some local operator on which U acts non-trivially. Okay, so that's where the zero form appeared here. Okay. I can guess what you're going to ask.
I mean, yeah.
You're going to ask about a charge conjugation in Chern-Simons theory? No,
Or many other examples of condensate operators where the symmetry is operators of condensate.
Yeah. Let me plead the fifth on that one. I'm trying to have a coherent structure. You can always make it more general, but I already excluded a bunch of things. I just exclude that one too. Okay. It's good. It's good. I think it's good to have a definition, even if you acknowledge that there might be interesting things that are not covered by your definition.
I mean, the reason to worry about that, right, is just that that's going to change your argument, or potentially change your argument.
I think you still can't have that in quantum
I
gravity.
agree with you.
But,
It's just
yeah.
Sorry, but in the Hogg-Kostler framework of the previous slide, what does local operator mean?
A local operator is right. So you take the region R to be contractible, and then it's in any operator that you can. Like,
Are you taking a limit, smaller and smaller sets?
yeah, smaller. You take R to be smaller. I mean, there's this issue of operator value distribution, which I'm not trying to hide, right? I mean, to be clear, I'm not saying that the Whiteman approach is wrong. So I think you do have operator value distributions, but then you build these
The
algebras out
Whiteman
of them.
approach, we have a local operator. It's in
Yeah.
the Hogg-Kostler that I'm trying to say.
No, but
So you want to take a limit over smaller and smaller
Yeah.
sets, all open sets around a given point,
That's right.
and get an algebra.
Yeah,
And that
I think-
limit and any element of that algebra.
Good. I think the best way to say this is what I mean is that for any region R, there's an element of the algebra that transforms under the symmetry. That's what I should say.
So it's an effectiveness.
Yeah. For any region whatsoever. Yeah. Go ahead.
Daniel, there are examples where you have a spontaneously broken abelian symmetry, and there's a current, but there are no charged operators.
So in my understanding of that, the U's actually still exist. We read about that in the paper.
Used to, but there are no charged operators.
No, of course there are. Right, in the Ising model, there's charged operators, even though the symmetry is broken. The spin.
Oh, yeah, okay.
Yeah, the thing people usually say is that U doesn't exist, but I disagree with that. I think it exists. The thing that happens there, so I suppressed a discussion of the continuity of the operator U as a map on the Hilbert space. Okay, I once gave a very technical talk about that to some mathematicians, but the continuity is different in the case of whether it's spontaneously broken or not. But all of this is true either way.
U is a linear operator. You mean continuity as a function of G? U is a linear operator.
No, it's a function of
It's a
G.
bounded linear
No, it's a function of G.
What?
It's a function of G.
As a function of G. Okay,
Yeah.
that's an issue.
Yeah, so if G is even a little bit away from the
Yeah,
infinity,
no.
it sends you to an orthogonal state in the Hilbert space, right? So that's the thing you have to deal with in the spontaneously broken case. Okay. Good. Right, so this is just saying we identified the group correctly. And then finally, so I like the energy momentum tensor too. I think it should be part of quantum field theory. That should be on the list of axioms. And so when it, in quantum mechanics, we say you should commute with the Hamiltonian, but in quantum field theory, again, we should respect the local structure. And so we should say it should commute with the energy momentum tensor. Which, again, has to be defined in some suitably distributional way. Yeah. Okay, so these are the rules. I like the
T
rules.
mu nu doesn't occur in the Hogg-Kostler axiom. So you have to say what T mu nu means.
I don't think Hogg-Kostler is the end of the story either. I think that the full set of axioms involves both Whiteman and Hogg-Kostler and the energy momentum.
No, but everything up to here was intrinsic to the definition you gave before.
No, that's
But
correct.
now you've introduced a new thing, T mu nu.
Yes, but I
So
think
you
I
have
need
to
it.
say what that means axiomatically.
Yeah, that's right. I agree with that. Yeah, but I'm not going to say it in this talk because the whole talk is not axiomatic field theory. Yeah.
Sorry, maybe you don't have to say them, but can you say T mu nu is uniquely defined if you include all of your axiomatic conditions? Can you say
I'm
that?
not sure if I want to say that because I think the tensor product is a natural operation on field theories. So I think you should be allowed to combine two non-interacting field theories and have that be a quantum field theory. So I don't want T mu nu to be
We
unique
could just take
necessarily.
what T is to be part of your definition of the theory, right? That's about
Well, I think there's a sense in which there's a preferred representation of the Lorentz group that acts on all of the fields, and that one should be generated by a T which is fairly unique. There's always the issue of improvement terms and so on, right? So
maybe
we have
you
to
don't
be
care
a
if
little.
it's unique or not. You just
What?
say this is what I call T, right?
Yeah, that's right. So you can say that, but Leonardo would impose a stronger condition, which is that there's no other t that is also conserved in spin 2 and so on. And so I guess I'm saying I don't feel the need to impose that.
Specifying t means you specify how it couples to gravity. Right?
Yes, that's correct. So I think there is a correct t for the theory. So maybe changing it is changing the theory, but Leonardo would ask for something stronger than that, right?
No, I'm simply saying of course, given two theories, we can always take the tensor product, but when we classify the algebras, sure, we can start with simple ones and then we can take tensor product and take direct sums. I mean, that's what I'm saying.
Yeah, that's fine. But then you might get new symmetries that when you do the tensor product. Yeah. Okay. So let's just talk about some examples. So phi goes to minus phi in phi to the 4 theories, global symmetry, of course. B minus L in the standard model. Okay, that's another example. It's more fun to talk about things which aren't global symmetries, so let's talk about that. So my favorite one that I always bring up is you can take the projection onto the 42nd eigenstate of the Hamiltonian and view that as a symmetry generator. It commutes with the Hamiltonian, but it does not respect locality. So this is the analog of like a discontinuous function from the point of view of this way of thinking. Okay, you shouldn't talk about it. Constant gauge transformations in Maxwell theory are also not global symmetries because they don't act faithfully on local operators. There's nothing that are charged under them. No local operator that's charged under it. There are things that are charged, but not local operators. Center symmetry in Yang-Mills theory, so okay, you all know that's a one-form symmetry, so it doesn't act faithfully on local operators. Spatial translations, of course, that's a space-time symmetry, so it moves the algebras around. I would say the bottom three here are different. So the first one is just bad. Okay, it's like discontinuous function. You just shouldn't talk about it. These three are all fine. They're just not internal global symmetry, zero-form global symmetries. So you need some other set of rules to describe them, right? So this is a global space-time symmetry. This is a one-form symmetry. This is what I'll call a long-range gauge symmetry. Okay, so they're all valid things. They're just not symmetries of the type we just discussed. Okay, and then the so-called non-invertible symmetries. Sorry, these are not symmetries. I will die on that hill. It's the algebra of topological surface operators. That's what you should call it. You shouldn't call it anything else. Okay. Which is that not to say that they're not interesting. They're just not symmetries. The algebra of topological surface operators is very interesting. Okay, so the symmetry is preserved. I need one other notion because now I'm going to have to go to the sphere. So let me just say something briefly about going to other spatial manifolds. Okay, so I'll say the symmetry is preserved on a more general Cauchy slice, with a different Hilbert space than one we were just discussing. If on that Hilbert space there's a set of U's which represent the group, commute with the energy momentum tensor, and actually that's going to be a consequence of this, which is that I demand that they act on the local operators with the same linear map that we had in RD-1. And so in general, the symmetry may not be preserved. You can have a mixed anomaly with gravity that breaks the symmetry. But if you're doing CFT and you're taking this to be the sphere, then since that's a Weyl equivalent to the plane, the symmetry is always preserved. And so we're not going to need to worry too much about that in this talk. We'll just go to the sphere without worrying about it anymore.
Well, in principle, there's some isomorphism involved in the Hilbert space associated with RD-1 and the Hilbert space associated with sigma.
Not always, right? I mean, it depends on sigma. If sigma has, cycles and so on, you can have new degrees of freedom there. But for the sphere, I think it's fine. Yeah.
There are a lot of strawman arguments that you're making. So I'll ask a different question here. What do you want a symmetry to do?
Well, I told you exactly what I wanted to do. So in quantum mechanics, there's a standard definition of the symmetry.
You gave a definition, but what do you think it should do for a quantum system? I mean, when we learn about symmetry, we like them because they give us some protection and selection rules, which they're the largest set of things.
So here I had the opposite motivation because when we say there's no global symmetry in quantum gravity, it's a contentless statement until we say what we mean by global symmetry. So in order to exclude something, I have to first define it. So that was the motivation here. I want to define the thing that's excluded in quantum
But
gravity.
there are extra selection rules that you can get, which is beyond just the definition that you're providing or the restriction that you're giving. So
No, I
do
mean,
you
so-
just not want to care about that, or
No, I have a finite amount of time, so I'm trying to work in the situation which is most familiar. I, of course, am interested in space-time and higher form symmetries. I'm not trying to litigate them away. It's just I don't want the talk to go on forever. So I thought this is the sort of the simplest general context where we can see the ideas. I think the ideas that are here are always correct. We just have to, make them, if we have one of these other examples in mind, then we have to go through and modify appropriately. But if I try to give the most general thing from the beginning, it'll be some categorical disaster, right? So, I don't know. I haven't yet reached that stage of enlightenment where all my talks are category theory. But, I mean, that's the direction you're pushing.
no,
me,
it
right?
is not the direction that
Yeah.
I'm proposing. I just want to understand what is the sort of a sharp statement about symmetry you want to actually kill in case of quantum gravity on.
Yeah, so I think the essential one is kind of, I mean, this one is kind of duh, right? So, and similarly this one, I guess maybe people would normally like to describe this by saying it's a topological surface operator. This is just a more algebraic way of saying it. Okay, so I think 1 and 4 are hopefully non-controversial.
No, nothing there is controversial. It's just I'm trying to understand the crazy narrowing down of everything.
Well, so this 1 and 4. So 1 is just quantum mechanics. 4, if I just put the Hamiltonian, it would have been quantum mechanics, but I think it's natural in quantum field theory to strengthen it to this, which is the same as saying you can deform the surface locally.
Okay.
Right. So, but I just more generally I want to say what it means for the symmetry to respect the local structure of the theory. Yeah.
To be clear, the only things that you're assuming that don't apply to things that other people are calling symmetries are maybe unitary, that excludes non-invertible symmetries.
Well, also things like time reversal that are anti-unitary.
Sure.
Right? Yeah.
So not an external symmetry, but yeah. And the point 3, right?
No, also point 2. Yeah.
Is it?
Yeah, non-invertible
People in
symmetries
QFT
break
talk
this.
about
Yeah, the so-called non-invertible symmetries violate this.
Okay.
Yeah. Yeah. Yeah, I mean, I actually think it would be great to have a list analogous to this one for non-invertible symmetries. Yeah, currently it's kind of it's the Wild West. Yeah. I'm going to talk about gauge eventually. As I said, I don't care if I get through this talk.
No,
I
but
just want to have fun.
let's get somewhere.
Yeah. I'm trying. Okay. So as Leonardo said yesterday, Noether's theorem suggests an additional property for symmetries in QFT, which doesn't obviously follow from the ones that I just said. And that's this idea of splittability, where you say that if you have a subregion R of the Cauchy slice, then you can have a unitary that in the region implements the symmetry and outside of the region does nothing. Now, again, if you want to be rigorous here, you should fatten out the boundary of the region a little bit and say you don't care what happens in the fattened boundary, but I'll suppress that. I'll just say that we won't say what happens right at the boundary of R with U. Okay. So there's some ambiguity at the boundaries, but I will say that if we have disjoint sets, then I want the product to be these to be the one where you just take the union of the regions.
So it's basically saying the symmetry operator is endable.
Yeah. Yeah. And so, of course, the motivation for this, as Leonardo said, is that if G is continuous and Noether's theorem is true, then you can construct this by just integrating the current over the region. Okay. Now, unfortunately, not all symmetries.
Sorry, that's a question.
Yeah.
Can you go the other way? So if you assume stability, can you prove the existence of a negative current?
Sorry, if I assume.
If you assume splittability of the symmetry, can you derive the presence of the current?
We tried, unsuccessfully. Because there are these annoying counterexamples, and you have to somehow litigate them away.
So there are counterexamples of splittable symmetry that don't have a current?
You mean splittable continuous symmetry?
Yeah, so the thing is, yes, because what can happen is so there's an issue of splittable on Minkowski space versus splittable on any manifold. So as far as I know, if the symmetry is splittable on any manifold, then I don't have a counterexample to where there's no current. But there are cases where it's splittable on Minkowski space, but not on other manifolds, and then it can't have a current. Yeah. But yeah, so what can happen is you can be splittable. You can be splittable in an annoying way, right? You can be splittable where there's some crap going on at the edge here, and then now naively you just want to shrink the region to extract the current, but you have to argue that the crap goes away in the limit that you shrink, and in these examples it doesn't. Yeah, so we had some example like that in the paper, essentially because the example has something that's non-local within the boundary of the region. Okay. So yeah, unfortunately, so Leonardo talked about this yesterday. So not all symmetries are splittable in quantum field theory, and in fact, there are continuous global symmetries which don't have noise occurrence. Now we can complain about the theories that have them, and that's fine. And certainly, it's a fun game to try to find a list of conditions which provably exclude all the counterexamples. And I would. So
I think the list that I gave yesterday doesn't provably exclude them, but yeah. I cannot think of a counterexample.
I agree with that. Yes, I agree with that. Yes. This is just a comment. So in fact, this issue is related to pi 0 going to gamma gamma, but I won't say anything else about it. So in this talk, I'll just assume that global symmetries are splittable nevertheless for two reasons. So the first being that, as far as I know, non-splittability only ends up being realized on spatial manifolds with non-trivial topology. Well, we're only going to study ST-1, and I don't know example that's not splittable on ST-1. And secondly, even on other spatial manifolds, as far as I know, and again, this is as far as I know, not a theorem, that you can always restore splittability by adding heavy degrees of freedom to allow you to end the surface operators. You know, if you're missing some charges, you just put them in with some heavy mass, and then you can split. Or you add some heavy strings or whatever you need.
What do you mean by non-trivial topology? If the sphere doesn't have non-trivial topology? The sphere has higher homotopy groups.
Yeah. I think I mean homology. Yeah.
Well, that's not zero homology.
Yeah. Okay, and so intuitively you can kind of think of this idea that everything should be splittable, and there's some trivial theorem about lattices where if you have a tensor product Hilbert space and you have a U where under conjugation, for an operator that's localized on just one of the sites, it always gives you an operator that's on the same site, then U is a tensor product operator. Now, that's not quite general enough because you would like to have symmetries that move it around a little bit, but only a little bit. And then the U should kind of, maybe can't quite be the tensor product, but you have this freedom of what happens at the edge. And somehow that's enough, I think. And so, yeah, and in this example, right, you just take the product of the subset of the UIs in the region that you want, and that gives you the symmetry in the region.
So does the comment that you just made imply that if you take the continuum of a theory defined on a lattice, that's not quite enough from this to get splittability?
Yeah, what I said here is what condensed matter people call an on-site symmetry. Mm-hmm. And so there, absolutely. But not all symmetries are on-site. And so I think there should be a generalization of this that accounts for that, but I did not put enough effort into trying to prove it, to actually prove it.
So this is more just some intuition?
Yeah. Okay. Yeah. Okay, now let's talk about gauge symmetries. Yeah. I'll put the quote on non-invertible, and you can put the quote on gauge. Right? All right, so we're interested in gauge symmetries because they're supposed to be dual to global symmetries in the boundary CFT. Okay, and Leonardo can tell us how a mere redundancy of description can be dual to something that's clearly physical. So, on the other hand, you're right. I mean, what does this really mean, though, right? I mean, don't gauge symmetries act trivially in Hilbert space? If you do a duality, doesn't the gauge group change, et cetera, right? This is what Leonardo was getting at. One thing you could say, which maybe is what Leonardo would say, is that you say, well, global symmetry on the boundary isn't really dual to a gauge symmetry, it's dual to something else. Okay. But on the other hand, certainly there are phenomena associated with gauge symmetry that's physical, like having massless gauge bosons, topological field theory at low energies. So there's clearly something physical there. And we just somehow want to pin down what that is without getting confused by the redundancy in the traditional approach to gauge symmetry. So our proposal is that what a global symmetry really is dual to is the asymptotic symmetry of a gauge theory which is in a phase that allows finite energy charges in infinite volume, sometimes called a free charge phase. So it's gauge theory. So gauge symmetry for me is a phase of matter. it's not a symmetry of a Lagrangian. So let me try to say it a little more precisely. So I'll say that a field theory in an infinite volume spatial manifold sigma has a long-range gauge symmetry. So this is a word that Hiroshi and I made up. If the following things are true. So so you should have a set of line operators labeled by representations alpha of G, which are called Wilson lines. Remember, line operators live in these annular algebra region, the algebras of annular regions that we talked about. There are boundary conditions at the spatial boundary such that for any subregion of the spatial boundary, there's a set of unitary operators labeled by elements of the group, and the endpoints of the Wilson lines that end in that subregion transform under the symmetry. And finally, finite energy charges are allowed. Okay, so here, this is some way of diagnosing finite energy charges. You turn on you insert a heavy background charge, and then you look at the thermal partition function and see if there are finite energy charge states that transform in representation alpha by integrating against the character of the representation. Okay.
Sorry, what are the brackets? The angle brackets?
This is the Euclidean path integral.
Euclidean path integral on what? It's S1 times sigma?
S1 times sigma, yeah. S1 times sigma. Yeah. Yeah, Tom.
That's going to have a UV divergence. What do you do with that?
You normalize it.
Okay, so you have to say something about the fact that this is actually, it's a UV divergence that's proportional to the length.
So the length, but the length is finite. Of course, it's the length in cutoff units. Yeah, in cutoff units is infinite. That's right. Yeah. But when you have a Wilson line, you're always allowed to renormalize away a length piece, right?
Yeah. No.
So I'm doing that.
But,
yeah. Okay, so the basic players are like this, right? So you can have Wilson lines that go from the boundary to the boundary. You can potentially have Wilson lines that go from the boundary to some charge operator. And then you have these boundary symmetry operators that live in a subset of the boundary.
Sorry, I'm still thinking about your criteria. I could tensor your field theory with an invertible field theory. Would that condition change?
Yeah, because you introduced, like, say if you introduce like the Z2 gauge. Oh, that's not invertible actually. I'm not sure, but I think if you introduce some discrete gauge symmetry, you can diagnose it using what I said.
So this is not a property of what you might call the projective theory.
No, it's a property of the theory. Yeah.
Depends on the superselection factor.
I'm not sure what you mean by that.
Well, like if you have a moduli space, depends on the gauge symmetry or not.
Right. The boundary conditions at infinity are part of the theory.
Right.
Yeah.
That sigma is not compact, right?
Yeah, it's not compact. Yes.
Yeah. So then
and
there's
that's
a whole
important.
issue of boundary conditions there.
Yeah, there is an issue of boundary conditions. Yes. Yeah. Okay. So this is a non-standard definition, but unlike the standard one, for example, it gives a well-defined answer to the question of does the theory in background X, or does quantum field theory X in background Y have gauge symmetry with gauge group G? So for example, QCD in R4 has no long-range gauge symmetry because there are no finite energy colored states. The standard model on R4, the long-range gauge group, so here you see the boundary condition dependence. If you allow monopoles, it's U1 times U1, otherwise it's U1. The gauge symmetry doesn't need to be fundamental, right? So if you do the CPN sigma model on R4 and the lattice, tuned to the critical point, it has a long-range gauge group U1, even though there's no gauge fields in the Lagrangian. QCD in ADS4, if the QCD scale is low compared to the ADS scale, has a long-range gauge symmetry SU3, where you have weakly interacting quarks and gluons in ADS. And then there's actually a phase transition as you vary this parameter, even in the presence of dynamical quartz, which I always thought is interesting, because usually people say it's a crossover, but here it's still a sharp transition. Another example is the Z2 lattice gauge theory with the fundamental Higgs field studied by Fradkin and Schenker, which has a long-range Z2 gauge symmetry in the free charge phase, but no symmetry in the Higgs phase. Tom did the U1 version of this. And then in a compact space, you never have a long-range gauge symmetry. Okay. Now, this is just because this comment came up yesterday. Sorry, Jake, I have to say this. So people sometimes say that this equals emergent one-form symmetry, but this is not true. In general, so for example, like if you think about SO3 gauge theory in ADS4, there's no center symmetry to speak of. but you still have a SO3 long-range gauge symmetry. And anyways, something exact, like a global symmetry in the boundary theory, shouldn't be dual to something approximate in the bulk.
Maxwell theory? Does that have?
Yeah. Yeah, that's basically this example. Yeah, so there's a U1 times U1. Yeah. Yeah,
So
for electric and magnetic charge. Yeah.
Should I understand your definition of having a gauge symmetry as just saying that when you have a boundary, you have some Gauss constraints?
It's related to that. The way I would say it is, people have spent a lot of time thinking about symmetries that act on local operators, symmetries that act on line operators. Okay. A long-range gauge symmetry is a symmetry that acts on a line which goes to infinity. So that's a new kind of object that people who only live in compact space don't like to think about.
Yeah, so if you have a boundary, if I have to impose some sort of Gauss constraint, then you should say I should think of that as having some sort of gauge symmetry that live in the bulk.
That's right, yeah. And
disappear.
this definition, because I wanted it to be a phase, I want it to be an infinite volume, but the definition is interesting even in finite volume, right? Like, say you just live in a space with a boundary. Then certainly you can have lines that end at the boundary. And this is a different kind of operator than operators that just live in the bulk. And so it makes sense to have a symmetry that acts on these but not on those.
That's completely correct.
Yeah, and so that's what I'm talking about. It's just that to make it a phase, I have to take the boundary away to infinity. Yeah. So for example, like if I did QCD in finite volume, you would have this symmetry even though it's confining, because you can just have a quark that's right next to the boundary and it transforms out of the symmetry.
But then these Gauss constraints can come in many different forms. Is there a way? What should I learn about?
Well, just like symmetries, there are many symmetries, right?
I mean, this is an additional. So, like for example, like in this Fradkin, Schenker, and Tom Eliezer story, right? There's some phase diagram like that, and historically, people didn't know what to say. What's the order parameter between the two phases, right? What is the what's the symmetry in one phase and not the other? But I'm telling you what it is. So you use it to diagnose phases, just like you would use an ordinary global symmetry.
But does it allow a room for the thing that you would call a gauge symmetry to not look like something you associate to a group? If it's just constraints that I have to impose on the boundary, that's not obvious to me.
Well, when you say, I mean, you can certainly have more interesting categorical things. Like you can have a global symmetry and a long-range gauge symmetry that mix together. That's certainly a thing that can happen.
Okay.
Yeah, that absolutely can happen. We gave some example in our paper. Yeah, Hodot.
One comment and one question. So for the Fradkin-Schenker, I think there's actually an order parameter that distinguishes the free charge phase and the Higgs confining phase.
Do you want to say the ground state degeneracy on the torus?
No. There's something called a Fred-Hagen-Markov operators. It's like a line operators, but then with two local operators sitting at the boundaries. That's actually order parameters.
Yeah, so I agree there's an order parameter. I would have said that the order parameter is this one. So maybe that's the same as what you're saying. I'm not sure. So it does have an order parameter. Yeah, it's just but people thought it didn't for a while.
And one question. So in the you said in the Maxwell case, there's two U1 long range gauge symmetry.
Yeah, I think it depends a little bit what you say about the boundary conditions at infinity. I understand best the boundary conditions that allow either electric or magnetic flux, but not both. In ADS, I feel like you probably have to pick one of those. In flat space, I'm less sure.
What about SO3?
SO3?
What about SO3 gauge theories? Like there are also top lines. Would you say there's also some?
Yeah, so again, I feel the most natural thing for me to understand is the one where just the Wilson line ends at the boundary, but not the Z2 TUF line. Maybe Z3, I mean, yeah. I think I mean Z2. I mean Z2. Yeah. Yeah.
We have little time. Can you hear about gravity?
We still have a half an hour, right?
You've been more than an hour.
Yeah, but we have an hour and a half, so I planned for an hour and a half. I'm encouraging the audience to participate, right? Drew.
So suppose I start with some quantum many-body lattice system and have a quantum many-body Hilbert space. How do I think about your long-range gauge symmetry defining this?
Yeah, it doesn't require the continuum limit. You can have it in a lattice system, but you have to be an infinite volume. So in the thermodynamic limit, you use the same definition.
Is there actually a requirement of having a unitary operator in the boundary? Can you think about some long-range non-invertible gauge symmetry? Or call it something else if you want to?
I currently don't understand how to gauge non-invertible symmetry. Maybe Shuheng can tell us.
Yeah, I mean, there are many works on it. You basically just sum over the topological.
So in the discrete case, I think I sort of understand it, but in the continuous case?
Well, we have very few examples of continuous non-invertible symmetry anyways, but I think for the discrete case, it's quite well understood.
Yeah, I think in the discrete case, I don't object. Yeah.
But can you have one that's long range?
Maybe. I don't know. I guess. I don't see why not. Yeah. Okay. So good. So Ivo complained. So right on time. Here's gravity. I feel like this part of the talk I gave so many times. You know.
No, but let's go.
Okay. So now let's say there were a global symmetry G in the bulk of ADS CFT. All right. So it will be represented on the CFT Hilbert space. So there's a whole story here that I won't get into, which is how do you generalize the definition I gave you in field theory to a definition in quantum gravity. And there are some subtleties you have to deal with because, first of all, the space-time itself is emergent, so what are you even talking about? But even within gravitational perturbation theory, local operators don't really exist. Everything has to be dressed using gravitational Wilson lines and so on.
There's some Hahn-Kostler formulation of quantum gravity.
Yeah, so there should be something like that, but I'm not going to dare to try to say what the axioms are.
First thing you said, so.
Well, I gave it for quantum field theory.
I know, but I mean,
Yeah.
I'm saying if you're going to generalize it to quantum gravity.
That's right. So we tried to do that in the paper to some extent, but of course our attitude was just to only say the minimal axioms that we need rather than try to capture them all because you're just going to get in trouble, I think, if you try to. Anyway, we're trying to rule it out, right? So we just want to have the minimal set of assumptions that are necessary to be ruled out. That's, by the way, kind of another answer to your question, right? Yeah. Okay, so I'm going to suppress this issue of dressing. Okay, you can ask me about it later if you want to hear about it. Morally, the definition is the same as the one that I said before, but it has to be fixed up a bit because there aren't any local operators. Okay, so modulo that caveat, if we have a global symmetry in the bulk, it'll be represented on the CFT Hilbert space by the duality. And by the extrapolate dictionary, since it acts locally on localized bulk operators, that includes the ones near the boundary, and so then it has to act locally on boundary local operators. And so therefore it gives a set of U of G comma sigma operators obeying the rules for a boundary global symmetry. Okay, that's not too shocking. If you have a global symmetry in the bulk, you have a global symmetry in the boundary. Right. Now, by assumption, in the boundary theory, global symmetries are splittable for the excuses I gave before. And so we also have these, or endable, or whatever you want to call them. So then we have these U of GRs floating around in the boundary theory. And then I claim that these are inconsistent. Okay. And so, you know, with apologies to Ivo, I have to say, you know, the definitions are the whole point of this business. Like, once you have all the definitions, it's like the argument is instantaneous. Okay, so it's all about understanding the definitions.
Wittgenstein would approve.
Wittgenstein, right?
I said there are no problems in philosophy, just a matter of using the right language.
I feel like this is something I learned. I feel like I learned from mathematicians, right? Math is really, you know, from an outsider,
I don't think I agree
freedom.
with that, actually. There are real problems, and you can't just define them away.
Yes. No, but it's about finding the right definitions, right? I mean, I feel like math is about finding the right definitions so that the theorems are true, right? I think this is correct. I don't mean that as a longer discussion.
Oh, okay.
I don't mean that as an insult. I mean this as a compliment. It's something I learned from mathematicians. Okay, so good. So let's see the contradiction. So by assumption, there's some object in the bulk which is charged under our putative bulk global symmetry. Some object. Because if not, then what is this symmetry? And so then we consider the algebra of an operator that creates this object, say right here in the center of ADS. This is a spatial slice here, with these boundary symmetry operators in a region that we talked about in the previous slide. Now the claim is that if we take the product, so if we split the boundary into three disjoint regions, R1, R2, R3, and we take the product of these U's in the regions, then at least up to some junk right at the corners here, we should just get back the unitary that implements the symmetry everywhere. If you don't like that argument, just multiply on the left by these three U daggers, Okay, and you'll get something that clearly does nothing in any of these regions except right at the edges, and that's the definition of U edge. Okay. Now, since each U of G comma R sub I is localized in the boundary, and so here's now, okay, so some people complained to me about this before, so here's where I'm going to bring in all the stuff that we learned about the emergence of space-time in the last 15 years. Okay, it comes here in this statement. So there's a lot of fine print in this statement, but I promise I have used this statement consistently. Okay? Since U of G R I sub I is localized on the boundary, it can only affect the bulk within the entanglement wedge of R sub I. An operator that is supported in this region cannot affect what's going on in the entanglement wedge of its complement over here, and that in particular, that includes this point. And since our charged operator is not in any of the entanglement wedges, it has to commute with all the U of G sub R's, and also U edge, because the support of U edge is measure 0. And therefore it has to just commute with U of G, and therefore the operator had to be neutral, and that's the contradiction, because we assumed that we had an operator that was charged under the symmetry. So the idea is very simple. It's just this picture. You can fit it on one slide, right? It's all about deciding whether you believe the words in the slide or not.
Right. So can I comment?
Yeah, please. Yes.
So here is my emotional problem with this. So what you have shown, elegantly shown, is that if we assume that the ADS quantum gravity is dual to a conformal field has this very strong locality property of splittability, then the conclusion follows. So how do we know that? That is the thing that needs to be shown.
Well, so we agree that it's dual to CFT, right?
Yes.
So the question is, how plausible is the splittability in CFT? And that's why I gave the first half of the talk, right?
Right, but the point is that you're really, quantum gravity is a mysterious thing. How do we know that the theory lives on the boundary obeys all the desiderata that we want to impose on quantum field theory? But certain things that are clear.
Oh, so if you ask how are you just saying how do we know that ADS CFT is true? Great question.
No.
Yeah, I have nothing useful to say about that.
No, your splittability here is doing a lot of work for you, and so I would be more satisfied with the kind of abstract nether theorem that was, at least for discrete symmetries, I don't know, but for continuous symmetries, we don't need all this complicated set of definition. There's a very sharp criterion. Is there an nether current or not? If there is a nether current in the boundary, then we agree that the symmetry in the bulk is quote-unquote gauge.
Yeah, I mean, that's the old argument. Yeah.
Which means, of course, that there's an asymptotic symmetry that survives.
Yeah.
So from the bulk perspective, I think certain things are clear more or less by construction. There is a conversion of Pareto Praltes function, blah, blah, blah. But the splittability property is an assumption.
Well, I think so. There's a. Let me think of how to say this. So, I mean, that's why I phrased it as a question about quantum field theory, right? I think it's a question that we don't need to understand quantum gravity to answer. We just need to understand in quantum field theory.
We're assuming that quantum gravity has this property on the bound, that this quantum gravity induces this property on the boundary. And I don't think we really know that.
Well, sorry, I thought we. Okay, I'm certainly assuming for this talk that ADS equals CFT, where CFT obeys the natural axioms of a CFT.
It obeys your natural axioms, but my natural axioms are more conservative. And so I think a real proof of this no global symmetry in quantum gravity would be proving abstract nether theorem the way I formulated it yesterday. If we could just show the existence of the nether current from the very basic properties of the Pareto-Praltes function, that I think would be a stronger argument.
I mean, there are lots of things I would like to show.
I don't disagree with anything you have said. It's very beautiful, but you have basically redefined the problem away.
Well, or you could say I reduced it to that if you want.
Yeah,
right?
you have changed the problem to showing that the theory on the boundary has this strong locality encoded in splittability.
But I mean, my experience. My experience as of 2017 is that everybody thought Noether's theorem was trivially true, and then I had to work to convince them that it's not.
Well, you should have talked to me.
Okay. All right. Yeah.
I'm very sympathetic to these comments, but I think even before the question, the technical question of splittability, I think there's the basic question of ADS CFT, and I'm sympathetic to taking that as an assumption, but I think what Daniel is saying is that, in some sense, no global symmetries is obvious if you assume holography. holography, of course, is a non-trivial.
No, if you assume this
I don't object to that. Yes.
And the comment I wanted to make is that if you have something which is not holographic in the usual sense, for example, an ensemble of CFTs or a generalized free field theory, then you definitely can have global symmetries in the bulk. And so I think it's really I agree. It's the locality of the strong locality of the dual.
That's right.
That implies that.
I completely agree with that. Boundary locality is the important thing here.
But the question is how strong of notional locality you want to impose, and I think it would be more desired. I don't disagree with anything. I'm just saying it would be, at least to me, emotionally more satisfactory to have a weaker notion of locality can show the existence of the nether current from that weaker notion. If it can be done.
So that's what I agree, right? So I tried to derive the nether current from my list of 4 things, right? But then I couldn't because they're counterexamples. And so then we need more things, maybe not on my list of 4 things about the symmetry, but we need more axioms about the quantum field theory.
To me, your 4 things are already too strong. I would like to dispense with splittability if it can be done.
Splittability wasn't on my list, right? No, that was, I had 4, I wanted to derive it from the 4.
Oh, yes. Okay.
Yeah. I think the 4 things I had are hopefully not controversial.
They're not controversial.
Yeah. So I think we agree. I mean, that was why the paper is part of why it's long, is we tried to derive it from those 4.
But you assumed splittability, right?
In the argument I did, but that's because I couldn't derive it from the 4 because of the counterexamples.
That's on your list. That's a number 5 on your list of axioms.
It's not part of my definition of the symmetry, but it's an assumption that goes into the theorem.
That's right.
Yeah.
So you're basically restated the question of existence, of non-existence of global symmetry as to the question of whether splittability is a property of the boundary city.
Yeah, but I mean, as you said yesterday, right? In kosher CFTs, as far as we know, it is, right?
Right, but that's
so it's not. I mean, I agree that we should try to prove it, just like we should try to prove that QCD exists. There are lots of things we should try to prove, but we should separate that from the question of what we think is likely to be true.
No. I completely agree that, in fact, that's the difference between physicists and mathematicians. Physicists is the truth. A mathematician is not really proving things that are obviously true.
Okay, you take that on with I'm going to touch that one with the 10th
Daniel, could you rephrase this proof in terms of a tensor network? I would feel much more.
Oh, I certainly can. In fact, actually, I think I should, because I have a proof that doesn't use splittability in a minute. So given that we're all fighting about it, maybe I should show that one. Yeah. So let me say, okay, so this is just to say there's no contradiction for gauge symmetry because there's a line that attaches the gauge charge to the boundary. This is obvious, okay? So no matter how much I do this, the line ends up in one of the regions, okay? Yeah, it's okay, I'll skip this. This is just saying that if you have a long-range gauge symmetry in the bulk, then of course you have a global symmetry in the boundary. That just follows from the definitions. Okay, so let me now give you, so we did actually have, okay, here, some people seem to be allergic to splittability. Okay. So look at the foresight here. So I want to mention there is an alternative version of the argument that doesn't use it. It has other things you can complain about, so there's a reason I gave you the first argument. But you can decide if you'd rather complain about these things more. Okay. So the idea is instead of doing this picture with the boundary regions, you have a multi-boundary wormhole. So you consider the CFT on a disconnected space, say with 3 boundaries, R1, R2, R3. So now I think none of you are going to fight with me about splittability when it's disconnected. Okay, if I have a sphere here and a sphere there, okay, I better be able to split the unitary into a unitary here and a unitary there. There's no UV issue of any kind. Okay. And then, at least as long as you believe that I can cook up a configuration in the CFT where in the bulk I have this multi-exit wormhole as the dominant contribution to the semi-classical description, and you believe that I can apply entanglement wedge reconstruction in the context of this wormhole, I can make exactly the same argument because this dot here is not in the entanglement wedge of any of R1, R2, R3. Okay? And so I have the same contradiction without having to use splittability. Yeah?
Do we have explicit geometries in ADS that do something like that?
Yeah. So in ADS3, there's a long literature about this. So we have some. Yeah. So basically, you do the CFT on a Riemann surface. So for ADS3, CFT2, there's a lot of, and then you try to study the phase diagram and argue that as you vary the moduli, you can get to a regime where this is the dominant.
But in higher dimensions, because in 3 dimensions, everything is a quotient of ADS.
Yeah, I'm not sure if the solutions have been explicitly constructed. I mean, I think we actually, Yeah, I don't know if they've been explicitly constructed, which is, that's one of the reasons why I used the other argument, but they probably exist. I mean, come on,
Did you need 3 sides as opposed to 2 sides?
Yeah, 2 is not good enough. You need 3. Yeah, because if you have 2, then you don't have this island in the middle. Yeah.
You could also put the green dot in a closed universe, and then you're good.
You can also try to make the argument that way. In fact, I'm going to say that something like that in a minute. Yeah. Okay.
I think in higher than 3 dimensions, these solutions, indeed, they've been they've been studied a bit. I think even Witten has a paper on one of these, but they're known to be unstable. Is that important for
Unstable in what sense? Like
like dynamically unstable?
Maybe I just need a Cauchy slice. Yeah. Okay, so so obviously this is a much more complicated system than the other one. That's why I gave you the other argument. But in this one, I don't have to use splitability. Okay, I'm actually on schedule. I was assuming not. I was planning not to talk about the gauging inversions, so I think we'll be good. Okay, so here I wanted to just mention. So another thing you could complain, right, is the original arguments from Hawking and Zeldovich. That there are no global symmetries. They use black holes, and they weren't just in ADS. And so, shouldn't we have an argument that more clearly is related to evaporating black holes, and which is something that feels more robust than just being in ADS? Okay. And so, indeed, Edgar and I at some point came up with I would say, less precise version of the above argument. That uses black holes instead of ADS CFT. And of course, it has to be less precise because, we know what the dual CFT is, but for a general evaporating black hole, okay. But nonetheless, there's some arguments, so I'll tell it to you. Okay, so here, maybe it's a mistake to even try to present this axiomatically, but I'll try a little bit. So say you have some quantum gravity system S, which has black holes in it. And then you have some reservoir system consisting of weakly interacting quantum fields, possibly linearized gravitons, et cetera. So this is a very concrete example is this thing that Netta and Ahmed and company studied, where S is some JT theory, or more generally some holographic CFT, and R is some non-gravitational bath. But there could be linearized gravitons in R. I think it seems fine. And then I'll just assume that somehow I can couple these together in a way that a pure state black hole in S makes Hawking radiation that goes into R. And moreover, that I can compute the fine-grained entropy of S and also subregions of R using the quantum extremal surface formula. Okay. And so here, of course, that's a huge assumption, right? Now because I didn't derive it from anything or whatever. I'm just assuming it. But okay, it worked in ADS, so maybe it works more generally. And then I'll also assume that this coupling preserves any global symmetries, and that the action of the symmetry can be extended to a local action on R. Okay, so this is all things that, roughly speaking, if you have a black hole S and it's evaporating to its Hawking radiation R, we think these things should be true. Okay. All right, so then here's the argument. So we just do the same contradiction again. So I've tried to shade the regions similarly. So this gray here, so I'm shading to match what I had here, right? So here I had these gray entanglement wedges in this yellow island. For the evaporating black hole, same story. So to the right of the dashed line this is a Cauchy slice of the radiation. This S here you can think is like the holographic dual of the gravity to the left of here. And after the black hole is old enough, what we learned from Netta and collaborators and also Jeff is that you have this yellow island here that becomes part of the entanglement wedge of the full Hawking radiation. And that's how the page curve turns over and goes down. Okay. So I won't say I derived that story in general here. I'll just assume that the story that they found works for general black holes. That's kind of the attitude of this paper, is we just assume black holes that evaporate always work this way. And then you just have the same contradiction. You split the radiation up into pieces, R1, R2, R3, etc. For small enough pieces, the entanglement wedge of the pieces is just these gray regions here. It doesn't contain the island. And also the entanglement wedge of S doesn't contain the island. It's just this exterior region here. But somehow if you have all of them, then it does, and then it's the same problem, right? So the global symmetry on the whole system is the product of U on S, and then the pieces of the radiation, and maybe some edge terms. But the green charged operator isn't in any of the entanglement wedges of the regions, so it has to not be charged, and that's the contradiction. Okay. And so now I didn't use ADS at all. I just used the unitarity of black hole evaporation, assuming that it works in the way that we learned from our friends. Okay. All right, now let's see. I annoyed some people. Let me see if I can annoy some more people. Sorry. So there have been several attempts to quantify the amount of global symmetry violation which is necessary to avoid the contradictions. So typically what you do is you start with some bulk Lagrangian that has a global symmetry, and then you find some wormhole which leads to apparent symmetry violation, at least from the point of view of the asymptotic boundary. And basically it's always because some global charge goes into a baby universe. Okay, and so then you sort of can't see it anymore, and you say the symmetry was violated. So that's fine, but so I have no. I mean, I believe these calculations. I think this is a fine thing to do, but this is not the dominant source of violation of the symmetries, right? This instead presumably comes from small black holes, which will give you terms in the Lagrangian that already violate the symmetry before you even think about wormholes. Okay. And those terms, maybe they'll be suppressed by a power of the Planck mass, but that's still much bigger than something that's exponentially small in the size of some, say the energy over m Planck. Unfortunately, the latter effects are completely uncomputable as far as I can tell. I don't know how to compute a small black hole correction to scattering at the LHC. It would be great if we could do that. That would show us these terms, but I have no idea how to do it. 1 sec, Miguel. And so for now, we're stuck kind of doing this former, so the former thing. So the advantage of this is it's reliable, right? Like you can compute these things in the semi-classical regime. You get an estimate that you can believe, but unfortunately, it's much smaller than the effects that you can't compute. And so I don't know what to make of it. I guess maybe that's why we didn't try too hard to quantify it. It's just we felt that there was this insurmountable problem that we didn't know how to say anything about. Okay, yeah, so who was first? Miguel was first.
Just wanted to say, like, in Gillian's talk yesterday, right, he had a sort of like, he had this lambda BH, which is a very reasonable way to estimate that, which is just take the formula from your first point and extrapolate to the smallest black hole that makes sense of effect.
Yeah, so you can try to do that, right? And you'll get some Planck suppressed thing, but then I guess what I'm never sure about is people tell me sometimes there can be moduli dependence that suppresses those terms. And I don't know, I don't have a good sense of, I mean, that gets into the whole swampland thing, right? Like, how far can you go off into moduli space and suppress this before something else gets important? And I would love to know the answer to that. Maybe Irena had something to say.
Yeah, I mean, I was going to say that you can actually estimate it in terms of what would be like the cutoff that depends on the moduli.
Yeah.
This cutoff, like the string scale or the time scale and so on.
Yeah.
And try to compare with examples. Tomorrow I can make some comments about it because it fits with examples in string theory if you do this extrapolation.
Yeah, thanks.
I guess I don't really understand this. I mean, if we're talking about a zero-form symmetry, it's going to be violated by higher dimensional operators.
Yeah.
So how do I say I compute those, right? Like,
well, you need the UV theory, right?
Yeah, but
you compute them. Like in string scattering, we can compute.
Let's say like let's solve quantum gravity.
Yes, that's right. That's why.
That's too hard, right?
Yeah. Hence. What did
So
I say? Uncomputable. Yes.
So how can I ascribe them to small black holes, right? I don't even see that.
Well, because when I say small black holes, I don't know. What do I even mean by what's a black hole whose entropy is 1 or 2, right? Like, is it different from a string? Like, I mean, there's just stuff that we don't understand that's small. Would you rather I said that? I'm happy to say that. But I mean, it's stuff that we can't reliably compute doing these semi-classical calculations, and so then I don't really know what to say.
I'm just not sure why we should have thought we could have computed it. But
did I say? Did anyone? I'm not saying anyone is wrong here, right? I mean, you compute the things you can compute. That's what these people are doing, and that's good. You should do it, right? But it's just unfortunately it's not the dominant thing. So
it should be pointed out that there are very old results of perturbative string theory that there are no global symmetries in perturbative.
In the continuous case, yes, that's right. Yeah, from your paper with Lance. Yeah.
Certain things that are true to all orders in perturbation theory and perturbative string theory.
Yeah.
So except for those, we know that there are higher dimension operators suppressed only by the string scale.
Yeah, that's right.
Okay, and then there's a question of the things that are suppressed only by e to the -1/g effects in string theory. And so those are the ones that we don't really know the size of the effect, though we can approximate it.
Yeah.
And if g is not small, which it probably isn't in the real world, those should be just suppressed by 1 over the Planck scale to
some power. Yeah, I mean, that's certainly my generic expectation, right? And so this thing where you take a Lagrangian with a symmetry and compute non-perturbative effects feels a bit artificial to me, because really there will be terms in the Lagrangian that violate the symmetry. And I wish I had something more positive to say about it, but
That's what I was saying.
I don't think we're disagreeing. Juvin?
Yes. So here you're trying to identify the symmetry violation due to gravity effect, right? And you mentioned two souls. I just wonder, say, even simple example like standard model, baryon minus lepton symmetry is violated by gravitational anomaly, right? In the sense that
I thought it's not.
that was already described on the
Yeah, you just said right-handed neutrinos.
Yeah, no, I was imagining with right-handed neutrinos.
without right-hand neutrino violated by trace algorithm.
Yeah. I mean, yeah, lots of. I mean, also baryon number and lepton number separately are violated, but so what?
But these are the gravity effect. So my point is that I don't require black hole even for this validation, or the standard model B minus L symmetry. So does that effect including the two sources of consideration you have here?
Yeah.
I don't need black hole, and I don't need wormhole.
But that's a standard field theoretic violation.
That's a sort of more conventional violation, right? Then you just say it's not a symmetry, right? I mean, I would just say it's not a symmetry even at the Lagrangian level, right? Like, yeah, just not a symmetry.
But that's anyway, that's gravitational effect.
So even for baryon number, which is anomalous with SU2, right?
No, that's different.
Higher dimensional operators are more important than the anomaly.
That depends on the theory, doesn't it?
I mean,
like, yes, generically I agree with
if
you.
you
But,
like go to the super K and you look for proton decay, right? It's not because of the anomaly.
I completely agree with that, yes. Yes. If it's just the anomaly, we're not going to see it.
My point is just that even maybe this, whatever you call the zeroth order or first order subleading order, the wormhole, black hole wormholes may not be even the dominant one. It's just some.
I mean, in general, they will never be the dominant one. The goal is to find the minimal breaking at least 1 to half if we couple the theory.
Yeah, I mean, the thing we actually want, right, is we want to know when we do neutrinoless double beta decay or we look for proton decay, we want some sort of lower bound on the rate, right? And none of us have that, right? At least, I mean, yeah, not at least not a bound that, I mean, probably we're not going to see it anyway, but it'd be nice theoretically to know what's the best bound on the rate, and I feel like we're far from that. I think that's all I'm saying here. Yeah, I don't know. There's lots of things. Mu goes to E gamma. I don't know. We can come up with lots of things where it would be nice to. Okay. So 5 minutes left. I had a few comments about gauging inversions, but I'll skip most of it and just kind of say maybe 2 or 3 slides about it. So far we talked about internal symmetries, and that's good because we had a lot to fight about. Continuous spacetime symmetries are kind of boring in gravity because they're always gauged, right? Just making the metric dynamical is going to gauge the identity component of the diff group. But what about spacetime inversions like R and T? Okay. So R sometimes people say parity. Parity only makes sense in even spacetime dimensions. So R means you reflect one spatial. That's how parity should have been defined in the first place. So, okay. So what about those? And in particular, what about CRT, right? So in ADS CFT, CRT has to be a symmetry by the boundary CRT theorem. Okay, you just rotate by pi in Euclidean signature. And in perturbative string theory, CRT is also a symmetry because you can rotate by pi in the Euclidean target space. So I interpret this as evidence that CRT is a symmetry of quantum gravity. It might not be true, but I'll bet that it is. And if it is, then it has to be a gauge symmetry because there are no global symmetries. So you can ask, what does it mean for CRT to be a gauge symmetry? And so I'll just make a few very brief comments about this. So in Euclidean signature, of course, there's a long history of gauging parity on the string world sheet, in the context of the unoriented string. So I have nothing new
Sorry,
to...
I'm confused. What if CRT is 1?
CRT is not 1. Yeah. You transform under CRT. Yeah. What?
It relates particles and antiparticles.
C might be trivial. I mean, you might be in a theory with no U1 global symmetry or something. But CRT is, there's no distinct, CPT and CRT differ by rotation and even in dimensions, and in odd dimensions you only talk about CRT.
I'm not sure that everyone agrees with, I think, parity is reflecting a single direction. I don't care what you call it.
Well, it's a definition, right? Yeah. I mean, I gave it a new name because I didn't want to say parity is something else because, okay, that's just semantics. But CRT is always non-trivial. For an energy momentum tensor transforms under CRT. Okay, so in Euclidean signature, there's a long history of gauging parity or R. But in Lorentzian signature, if you try to gauge things involving T, it's kind of confusing. Okay, so let me just make a few comments about that. So for example, here's a twisted state. Here's a state in the twisted sector of gauging time reversal. It's called the Lorentzian Mobius strip. You go around the circle, and when you come back, time is reversed. Okay, so that's a valid contribution to the path integral in a theory where T is gauged. And, okay, I mean, come on, right? Like, is this okay? Like, can you even talk about quantum field theory and space-time like this? So Tokiro and I wrote a paper saying that indeed you can talk about quantum field theory in a space-time like this. And in fact, in the bulk of ADS-CFT, it's necessary to include such configurations, or you can't match calculations that you can actually do in the CFT. So you have to include them, which is good because CRT is a gauge symmetry, so you should include them. Yeah?
If CRT is gauged, do we have a CRT Wilson line?
Yeah, it's a bit subtle because it's a space-time symmetry, so I'm not totally sure how to answer that question. You certainly have a holonomy of CRT. Like this is a configuration where there's holonomy for T as you go around. And so I can certainly, there's a degree of freedom that tells me whether or not there's holonomy for CRT. Yeah. So in that sense, yes. I'm not totally sure if it behaves like an internal Wilson line in all respects because it's a space-time symmetry.
The reason I'm asking is because generally if you want to get rid of the discrete global symmetry, and by gauging it, that doesn't do the job.
No, I know, but I think it's
another global symmetry.
Yeah, so we talked about that before. So I tried to run that construction for CRT and it didn't work.
So meaning that it isn't a dual.
It doesn't generate a dual.
Do you consider this a long-range gauge symmetry?
Yeah.
Yeah. Okay.
Yeah. Yeah, I mean, it's the space-time version. So I told you the internal version before, but it's the space-time version. Yeah, so like in ADS-CFT, right, there's a global CRT symmetry in the boundary theory,
right,
which you should think of as being generated by the CRT flux at infinity.
Can you argue that all the funny non-orientable stuff is always behind horizons or something?
Yeah, so that's good. That's kind of why it's okay, right? So basically that's why it's so consistent with boundary causality, is because all the stuff like this ends up being behind horizons so that it doesn't violate boundary causality.
Is there like general argument proof, or it's just like checking that case?
Right now there's not a general argument. There's a conjecture called chronological censorship, which is a cousin of cosmic censorship, which would say that it's true, but just as cosmic censorship is not yet a theorem, I should end, but yeah, go.
The CRT transformation in quantum field theory acts antilinearly. Is that antilinearity reflected in
Yes.
how?
Well, okay, that's a little more technical than I was planning to skip all the details about this, but essentially the symplectic form has a discontinuity as you go around the circle, which I think is a manifestation of that.
When you go to its opposite.
When you write the canonical commutation relation, there's a phi dot here. So when you try to do field theory on this background, you have to say which direction is the dot, and when you go around, right? So somewhere you have to hit a discontinuity.
So this has to do with the fact that the time changes on the two sides of the black hole, right?
Well, here I'm just doing quantum field theory on this, but but there's an avatar of that in what you're saying. Yes.
You said it always happens behind the horizon.
Oh yeah, I think it's related to that. Yeah. Okay, so I want to skip all this. I'm now over time. I should be punished. So I just wanted to have one more comment. So this is the match in ADS-CFT. I matched some Lorentzian Whiteman correlator in this funny time non-orientable geometry to a correlation function in the Ising CFT. here's this stuff is behind horizons. Okay. The only other comment I wanted to make, and then I'll really be done, is in the context of quantum cosmology. So if you gauge a symmetry involving T, because it's antilinear, as Dan just reminded us, it has a funny consequence for the Hilbert space of the theory. Because in a closed universe, all the physical states have to be gauge invariant, right? That's familiar from Gauss's law in electromagnetism. The same is true for discrete symmetries. And so for an anti-unitary symmetry, this implies that the Hilbert space is real, because if psi and phi are CRT invariant states and you do a linear combination, if you have complex coefficients, then they transform, and it's not a CRT invariant state. I forgot to close the cat here. So A and B have to be real. So the set of CRT invariant states is real. So the Hilbert space of a closed universe is real. So this is, I think, a strong constraint on any holographic dual of cosmology in a closed universe. Now, in fact, not only is the Hilbert space real, it's probably one-dimensional. But it's real and one-dimensional. Okay, and so that's another talk I could give, but I won't give that talk now. Instead, I'll be done. Thank you.